Hello everyone, my name is Tushar Rana and I am from IIIT Sricity and I am a second year undergraduate student doing BTech from CSE. So we have started our chapter that is coordination compound in the previous lecture. Okay, so we have covered some important parts related to basic intro and we have also discovered the isomerism part. Okay, so it is also a big chapter, so I thought to take more classes. So let's start coordination compounds. This is part 2. Okay, so in this lecture we will discuss some of the concept related to bonding in coordination compound that contains basically the valence bond theory. You have heard about this, and crystal field theory and ligand field theory is normally uh, not taught in that 11th class. Okay, so it will be our new part, this one. So we will focus on this. Okay, let me take out my marker here. Okay, so this one and this two, we will focusing on this two. Okay, don't know why it is not. Okay, wait, just wait a minute. Okay, sorry for the technical problem. It was some error come here. Okay, we have resolved. So I was discussing about that we should be focusing more on this crystal field theory and ligand field theory. Okay, so just mark this two. Okay, this one and this one. Now, and you have heard about this molecular orbital theory in the previous class. Okay, so now let's start our chapter with the basically valence bond theory. So we will discuss that is bonding in coordination compounds. Okay, so what is this bonding in coordination compound? Okay, in the previous class we have seen some of the structures of that ligand and metal ion complexes, like we have seen NiCl4. Okay, NiCl4, that was a complex part. Okay, so we have to we were making some structure related to this, like Ni or Cl, like this. Okay, so how these bonds are formed we will see here in this lecture. Okay, so coming on to the first part, that is valence bond theory, or commonly known as VBT also. Okay, so in the inorganic classes you have heard about this. So let's start with the intro. Linus Pauling, 1931. Okay, this scientist has discovered about this theory. The valence bond theory satisfactorily explains the structure and the magnetic properties of a large number of coordination compound. Okay, for a large number of coordination compound, it is satisfactorily explainable for the structure and magnetic properties. Okay, okay. So let's move on to the some salient features of the theory. The required number of vacant orbitals for accommodating the electrons vacant or a complex vacant SPDF. Okay, so what this is saying? This is saying that in that complex compound, we have a structure like this NiCl4, and this is a metal atom ion, and this Cl are ligand ion. Okay, So the number of vacant orbitals for accommodating the electrons donated by the ligand. Okay, so like it is a d block transition element, so it will contain some d block, some d orbitals, okay, which will be filled by this electron contribution of this chlorine ligand and this Ni ligand. Okay, so due to this, there is a coordination number also, like here coordination number comes 4. Okay, so it will come into a picture. Now let's move on to the next part. Some more features of this VBT theory is this vacant orbital goes hybridization to form same number of hybrid orbitals. Okay, each ligand has at least one orbital containing lone pair. True. Like this Cl also, it will have at least lone pair also. Like this is 7. So like Cl, you know the structure. If it is bonded to one bond, it contains 7 pairs, or sorry, 4 pairs of 3 pairs of lone pair and one that is participated into the bonding. Okay. Now vacant or hybrid orbitals filled with ligand to form coordination bond. Okay, as you know that if it will have to form the bond, it will use its vacant hybrid orbital only. Now coordination bond it stronger if the overlapping between the orbitals is greater. Okay, so you have to mark this term in your notes. If the overlapping between the orbitals, like if there are d orbital, okay, if it is d orbital, okay, and there are some other f orbital. Okay, so if the overlapping between the orbitals is greater, then the coordinate bond that is formed is will be more strong. Now let's move to the next part. The vacant orbitals of the metal atom ion undergo suitable hybridization to yield a set of equivalent hybrid orbitals of definite geometry. Okay, so this statement is saying that if we have to form that coordinate bond, then the vacant orbital of metal atom ion and that ligand will undergo certain hybridization. Okay, so there will be some some interconnection between the hybrid orbitals, like this. If we take the example of cobalt, cobalt has a +3 oxidation state in its coordination compound. Okay, so this is the structure, or this is the, or we can say this is the orbital structure, orbital diagram of d, because it contains most of the valence electron. Okay, and this 4s and 4p orbital are vacant. Okay, as you can see, we will not go much deeper. We just need to see this 4 orbital. Why? Because the coordination number for cu is 4. Okay, why 4? Because in the compound we have given like co, if some ligand is x and it is 4, so this is the coordination number equals to 4. And cobalt has a +3 oxidation state due to some anionic part outside. Okay, now we need to fit this 4 ligand into this vacant orbital and also maintain this hybridization. Okay, so it will result into formation of different structures. Okay, so depending upon the geometrical shape and hybridization that was given, it will have different structures. Like okay, the next part is that only geometrical shape depend upon the hybridization of the metal orbital. Okay, if there will be a different type of coordination compound, and each will have different hybridization, so their structure will also be different. Okay, like if someone has lone pair on the central metal ion, their oxidation number is different and coordination number is different, so different hybridization, different structure will be formed in accordance to that. Okay, okay, you can refer to this table. I have given some examples also. Like if the coordination number of the central metal ion is equals to 2, so the hybridized orbitals will be sp. How? Because it will form a linear structure. Like if in the case of AgNH3 whole twice, uh, AgNH3 whole twice, that is positive charge come up. Okay, so what can be the structure? Like this is Ag, NH3 can be bonded like this and this. Okay, and Ag +3 charge, NH3 equals to 0, so Ag can plus here also. So this type of structure will be formed. Now moving on to the sp2 structure, we have a hybridized structure with a coordination number equals to 3, so it will be trigonal planar, HGI3. You all know what is trigonal planar. Now, if four coordination number that was tetrahedral only, sp3, there are many. Okay, it's like I have also given the example that was this one only. This X is basically halogens. So see, this will form a coordination number four of that tetrahedral structure. So depending upon the different coordination number and different hybridization, it will form different structure. That only this table is trying to say, like DSP2 and DSP3. Okay, so in that 11th class, you have heard about sp3d, sp3d2. Okay, but you have not heard about dx square minus y. Sorry, DSP. Okay, or DSP2. Now let's move on to the next part. If n minus 1 orbitals are used for the hybridization, the complex is called inner complexes and ND called outer complexes. Okay. See, it is saying that if n minus 1 d orbital, if it contains n number of subshells and a subshell lesser than the highest subshell is used for the hybridization, the complexes are called inner orbital complexes because it is using the orbital which is prior to the max vacant orbital. Okay, what I'm trying to say is that like if we have outer orbital as 4D, okay, but it is using 3D. Okay, see here 4 n minus 1 equals to 3. Okay, so 3, if this orbital is used in the hybridization, then this type of complexes are called inner orbital complexes, and these are also differentiated by low spin or spin paired complexes, and vice versa. For the outer d orbital, it is outer orbital complexes and high spin and or spin free complexes. Okay, so you need to learn this one. Now talking about the ligands. Okay, now you have heard about how the structure are formed, how ligand are connected with the central metal ion. Okay, now let's see what are the ligands. Ligands. Okay, you all know what are ligands. Ligands are generally types. Okay, what I'm saying. This is weak ligands, and strong ligands. Okay, so there are two types of ligands. Okay, weak ligand and strong ligand. Okay, you can insert one more type, that is moderate or medium. Okay, medium. It is weakly ligand or strongly, both doesn't matter. Okay, now when talking about strong field ligand like NH3, you can note in your notes that NH3 and Cn negative are the strong field ligands, are involved in the formation of complexes. They causes pairing of electrons. Okay, this is the important statement you have to highlight. If strong field ligand are involved in the formation of complexes, they causes pairing electrons in the metal ions. Okay, this process called spin pairing. So you need to check this one. Now, structure of complexes compound based on the VBT. Now we have heard about what type of structure can be formed or based on the hybridization. Okay, now talking about VBT theory, how the complexes compounds are formed. See, structure of NiCO4. If we take the example of NiCO4, NiCl4, NiCN4, okay, this whole are a tetrahedral. Okay, tetrahedral, or we can say not tetrahedral, coordination number equals to 4, and these two are coordination number 6. Okay, so in this chapter we will more focus on coordination number 4 and 6 only. Okay, because most of the questions come from this only. Now here we have given an example of second question, that is formation of NiCl4. So how this NiCl4 minus 2 minus complex compound hybridization occurrence structure is formed. See, oxidation is +2. Okay, you can see how this is NiCl4 and whole complex is -2. So you can equate equals to Ni is equals to plus X plus -4. Okay, so if you will equate this one, then X you will get equals to +2. So nickel oxidation state of nickel is equals to +2, like this one. Now, if Ni is plus 2, so on writing the electronic configuration, you have to remove the two outermost shelf electron. Okay. So it will have an electronic configuration of not Ni, it is Ni plus 2 electronic configuration. What electronic configuration it will acquire? 3D8. Okay. Okay, it is written 4s2. So, but for ns2, we will remove that 4s2. Okay, it will not be counted. It will be removed. Okay. Now, paramagnetic contain two unpaired electrons. Okay. See, this is Ni2 plus ion. We have eight electrons in the outermost orbital, that is d orbital. 1, 2, 3, 4, 5, 6, 7, 8. You can count. Now, we need four pair of um, vacant orbitals to form the NiCl4 complex. Now see, this two can be used for this one, okay? Or we can use both this one, okay? If we will use this one and this one and this one, so it will be very energy difference, and it will create instability also. Like if we take from one from here, one from here, one from here, and one from here, it will be not good. But if we take the whole outermost orbital, this whole four, and keep calm this one, so this will form a S, this S, like how I will say, okay, like we can here 4s, one orbital, okay, one electron from here, and from this p, 4p, we can take 3, so we will get 4, which will accommodate to 4Cl. Okay, so 4 pairs of electrons from Cl will be given here for the hybridization, and as it is outermost orbital, so it is high spin complex. You have I have taught that one. Okay, now similar to that NiCN4 and NiCl4, similar like that, Cn is a strong field ligand, first one. You have to check like this one also. Now see, dsp2 hybridization, 4 pairs of electrons from the Cn negative ion. So if the strong field ligand comes in the picture, so we will use the inner orbital complexes, okay, that we have left in the first example. This one will come to here. Okay, now this whole block is empty. We will use this one block, this one block, and this one block. So it will let's say d s, and we use 2p orbitals, so dsp2. Okay, so dsp2 hybridization will be occur for this NiCN4 minus and okay, and this NiCl4, we have checked that it is sp3, that is okay. But now, and I have also told that for strong field ligand you have some exception also, so that one only. Now let's move on to some of the drawbacks of this valence bond theory. It does not explain the color of the coordination compound. Okay, this one is also a topic in our coordination chemistry. We will check it out later. Now, cannot explain magnetic behavior on the based on geometry. Does not explain why some called inner and outer complexes same metal ion in the oxidation state. Okay, fails to predict the exact geometry of the complexes with the coordination number of 4. Okay, just as you have checked here in CN case, this is dsp2 giving different structure. Okay, like that. Here are the some example. This is according to valence bond theory, and this is according to X-ray analysis. These are not same. Okay. So the practical implication of this theory is not correct. So it is a major drawback. Now, moving on to crystal field theory. Crystal field theory. I told you that the crystal field theory is more important. Now let's see one now. The crystal field theory was proposed by Hans Bethe and Van Leck. Okay, there were two scientists which shown this theory. Now, crystal field theory assumes that the interaction between metal ion and the ligand is purely electrostatic. Okay, what is the main funda behind this theory is crystal field theory assumes that the interaction between metal ion and the ligand is purely electrostatic. Okay, so here electrostatic came into picture. So you have to focus here. Now, some of the features which are differentiating the crystal field theory from the valence bond theory are central metal atom ion, or okay, is surrounded by various ligands which are either a negative charge or neutral molecule. Okay, so it is also quite clear that the central metal, sorry, central metal atom ion is surrounded by the ligands which are negative, or it can be neutral also. I have told that one also. Now, electrostatic interaction between the ML metal ligand. Okay, it is example. For example, it is Fe and CO3. Okay. Now, central metal atom have 5 degenerated orbital. Okay, it is true that if we have a d orbital, okay, 1 2 3 4 5, so this is dxy, dyz, dxz, dx square minus y square, dz square. Based on this different degenerated orbitals, we have different structure regarding that one, like that. For this, if we start from dxy like this one, okay, it is simply what it is simply double tumble shape, but with between the axis. Okay, not on the axis, it is between the axis. See, this is y, this is x, this is y, and this is x, and between the axis there is this double shape. Okay, it is two types. Okay, now similar to yz, just you need to make the axis different. Okay, now there is different about dx square minus y square and dz square. So dx square minus y square is similar to that dxy, but here the orbit, the double shaped structure is not between the axis; it is on the axis. See, this is the axis, this is the axis, and shape is over this one only. Okay, it is passing from this one only. So it is creating a difference. And now dz square. Dz square is simply z. This is y. This is x. So this one will be z. So in orientation of Z, there is a dumbbell shaped single and surrounded by a spherical. Okay. Now it can be asked like what is the structure of this degenerate orbits? You can say this like that one. Now, salient features of CFT. When the ligand approaches the metal ion due to the repulsion force, as you know that it is electrostatic force dependence in the CFT theory. So this is the repulsion due to electron also. Okay, the degeneracy of d orbital is destroyed and they split into two groups of energy level, that is only high energy and low energy, and we name it as a T2G and EG. The effect is called crystal field splitting. So if the orbitals, sorry, if the metal atom ion due to the repulsion force comes in the contact and there is a degeneracy of d orbital, so it will destroy into two parts. First one is that EG energy level, and second one is T2G energy level, and the difference between these two energy barrier, okay, this is known as delta naught, which is known as crystal field splitting effect. Okay, which we measure by Decker. Okay, now for this isolated atom ion, it is on this initial state, but when it comes in the crystal field, okay, it will dissociate it into this dx square minus y square and z square. So this will be part of Eg, and dxy, yz, and dz T2G. So it is a lower energy and it is a higher energy, you can see. Now, some more features are there. Due to the repulsion, the orbitals along the axis of the ligands acquire the higher energy, while those lying in between the ligands acquire less energy. Okay, so I was telling about that diagram because that if this statement you will read now without that explanation of that diagram, you cannot understand. Like, see, it is written here. Oh, wait, I mean, let me highlight. It is written here. The orbitals along the axis of ligand acquire higher energy. Okay, see, what are the along the axis? Along the axis are this dx square minus y square and this z. See, it is also along the x square, along the axis. Okay, and it is saying that this axis orbitals have higher energy. Okay, let's see. See here, this Eg is upper. Okay, s square minus y square, so it is a higher energy level. So like this, you can relate. So it is important to read each and every part which are given the slides. Now, okay, it doesn't show the overlapping true. From the crystal field stability energy, the stability of the complexes can be known. Okay, we will discuss about the stability stability of the complexes later. Okay, we will discuss about this in later part. Now, what is the definition of this crystal field splitting? This crystal field theory was different, and this splitting is different. Splitting is basically that if we have given an isolated complex compound of that coordination compound, so when it will split and split into that uh, T2G and TEG set, okay, five there will be 5d orbitals, okay, maybe three up, okay, two down, or two down, two up and three down, based on the different stabilizing different stability of the ligand. Okay, now crystal field stabilization energy, it is also a important part. Now, change in the energy achieved by filling up the electron in the orbital in the complex metal atom. So it is generally saying that crystal field stabilization energy is just the difference or change in energy achieved by filling. If we fill the upper electron first, or if you fill the lower electron first, and the difference between that energy, where energy is only the crystal field stabilization energy. Now, for calculating this, we must focus on this high spin complexes and low spin complexes. You all know what are high spin and low spin. That is based on the VBT. Okay, you have seen greater number of unpaired electrons and hence higher value of resultant spin and magnetic moment is called that higher spin complexes. Okay, now calling about low spin complexes, just vice versa according to that. Now, what is pairing energy? The energy required to pair two electrons against the electron repulsion in the same orbital of the metal atom. Okay, there is nothing to discuss about that. It is generally clear just by reading. Now, some of the application of this crystal field theory. For first, we will take the tetrahedral complexes and we will move on to the octahedral complexes. In tetrahedral complexes, MX4 and the metal atom or ion is placed at the center like this one, and the regular tetrahedral and four ligand are just placed here, 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 and here. Okay, at four corners of the tetrahedron. See, this is just diagonal opposite. Now, ligands approach the central metal atom in between three coordinate axes, that is x, y, z. This is a simple structure model of the tetrahedron structure. Now, but if in case we have some strong field ligands or some weak field ligands, we will have a energy difference there. In strong field ligand, the electrons prefer to pair up in EG. See, the first pairing will be occur in EG orbital, giving low spin complexes, while in case of weak field ligand, it is preferring to go on T2G, that is higher energy set. Okay, what I am trying to say that there is a degeneracy is obtained when splitting. If we have like NiCN4, okay, CN is a strong field ligand. Okay, so it will so the electrons of that CN ligand will try to pair up with EG set, that is this one, this set, and the other one, that is weak field ligand, will go to the T2G set. And the difference between them is like calculated with this formula. I will tell you the formula also. Okay, this was the free state. Okay, now what is trying to say? Giving more unpaired electrons and hence form high spin complexes. Okay, it will, if it is up, then low spin complex. It is high spin complexes. It is low spin complexes. Just technical terms only. Okay, these are the some energy barriers value given 2 by 5 of delta T. This whole is delta T. This is energy difference between T2G and EG. And the base, okay, base distance from the this middle to this high energy, that is T2G, is 2 by 5 delta T. And the below one is 3 by 5 delta T. Now, moving on to the octahedral complexes. I will tell you what about that one. If you have a compound like this one, okay, this one is the structure, 1 year, 1 year. Okay, you have heard about what is the octahedral structure. Okay, two orbital dx square minus y square and dz square are axial greater repulsion and dxy. Okay, see, dx square minus y square and dz square have a axial repulsion, while the dxy and dyz and xz have less repulsion. So it may also ask in a question. So just remember this point. Now, 5d orbital lose degeneracy and split into 2 points. Okay, the group T2G lower energy while EG group have higher energy. Okay, I have told this one only in the tetrahedral structure only. Okay, the group T2G will have a lower energy while the EG group will have a higher energy. You can see here also. See, okay, here based on the ligand it is different, but here you can see this T2G has a lower energy, but this EG is a higher energy for this octahedral. But for tetrahedral, it becomes different. This T2G is a higher energy, but this EG is a lower energy. Okay. See, EG we have dx square minus y square and dz square, and that T2G is equals to dxy, dyz, and dzx. Okay. So it is a difference between the tetrahedral, octahedral degeneracy orbital structure. Like for octahedral, we have the lower energy as T2G, while in that tetrahedral, the lower energy is EG. Okay. Now, some of the application related to crystal field theory to octahedral complexes are experimental calculations show that the energy of the T2G orbital is lowered by 0.04 delta naught or zero 0.04. Okay, this one is only that one only. What I'm trying to say, see, I have shown you a table. Okay, if you calculate this 2 by 5, it is generally 0.4 delta T. Okay, or we also seen that it is also written as 0.4 dq. Okay, and this is 0.6. So just it is written more decimal form for the, and the energy of EG orbital is increased by delta of 0.6 and 6 dq. Okay, this is for octahedral because the energy because the orbitals, that is T2G and EG, are different in both the structures. Now, thus the energy difference between T2G and EG orbital is delta naught or 10 dq. This whole, if we add this one, it will add up to 10 dq. Okay, that is generally multiplied by 10. Okay, which is crystal field splitting energy. Now, CFSC increases with the increasing strength of the ligand. Okay, if we have the most strong ligand, then the crystal fields splitting energy will also increase, and the oxidation state of metal ion increases. Okay, so these are the two factors which are, or I can write here only. Wait, factors affecting CFSC. What are these factors? So CFSC is proportional to strength of ligand and also proportional to oxidation state of central metal ion or atom. Now, there are certain limitations also to this crystal field theory. It does not explain the S&P orbital. Okay, just you have noticed that I was discussing just about D orbital only, not S or P. So for this, it is a limitation. Does not explain pi bonding as P orbital not there. So why P bonding? Cannot explain partially covalent nature of the metal ligand bond. Okay, spectrochemical series. Okay, we will discuss about this later. Moving on to the stability. Okay, I told you that we will talk about the stability in the later part. Okay, just move. Okay, wait. Let me take a new page. Stability of coordination compounds. Okay. So if we are making some certain compounds by the different hybridization of this valence electron of this ligand and metal ion, okay, there will be certain defect in the stability or certain questions about the stability of the product formed because we can form different structure also, as we have seen in the isomerism part also. Okay, but that was regarding the VBT only. Now, see, stability of coordination compound. We will also have some stability constant here, I guess. Okay, thermodynamic equilibrium constant. Okay, see, you all know what is thermodynamic equilibrium constant. Stability depends upon the interaction between the metal and ligand. Okay, I was talking about that one only. Okay, if the interaction strong, thermodynamically stability will strong. Okay, it is just saying that if interaction will be strong, then the thermodynamic stability will also be strong. That is resistant to that heat or temperature or different condition related to the thermodynamic nature. Okay, now reaction between metal ion and ligand is based on Lewis acid and base. Okay, as you know that central metal atom or ion is equals to Lewis acid. Okay, and while that ligand is Lewis base. Okay, so we have to check the stability of these two, so we can conclude the stability about this our compound. Now, the greater value of the stability constant, more is the stable complex. Okay, so we can calculate stability using that stability constant. Stability constant. Okay. Now, what is the complex? Like if we have a given complex compound like M plus N times N, this is metal ion and this is ligand. N is basically the coordination number. This is some case and MLN. This is a complex compound form. So we will apply that formula, that general formula of this chemical equilibrium, MLN divided by M and LN. Okay, as L is N times, so it will be N times here power. Now, what is the key? Key is the formation. Key is the formation equilibrium constant. Equilibrium constant. Okay, and this K is only determining the stability of complexes. And what is K dash? Okay, I have written. I guess it is written. See, as it is a reversible reaction, so just reverse it. So on reversing, we will get K dash is equals to 1 upon K. This is all related to chemical equilibrium. And this K dash is instability and constant or the dissociation constant. Okay, so easy. Now we have some stability values of the coordination compound. For example, first one is CD plus 2 and 4 NS3. This is the coordination compound and the stability is 1.3. Okay, similar for AgNS3 4 2. This is 1.6. Okay, you can check it out. I have just given some example. If you are having any doubt how it can be expressed in terms of this integer, so like this we can express. Now, Ca negative is a more stable than amine complex. Okay, for this it is saying this Cn. Okay, so that's why there is not Cn come to picture. We have NH3 here. So it concludes that the cyano is stronger ligand than amine. Stability depends upon the charge density of the central metal ion. Okay, and the nature of ligand. We are discussing this one only from the start of the lecture only, that both central metal ion and the nature of ligand are responsible for the different structure and different hybridization okay formation. So till now we have completed our half to 80 to 90% of the chapter. Okay, that is bonding, isomerism, okay, CFSC, crystal field theory, VBT, and all that. Now let's it's time to perform some of the questions. Okay, so let's solve some of the questions related to coordination chemistry which were asked in the JEE-Main's previous year questions. Okay, so I have taken a PDF here only. So I have taken it from the Anti-Abhyas. You all know what is that Anti-Abhyas. It is a website and it also came in app form also. So here you can check it out. Okay, so we will discuss some of the problems which we have not done yet. Okay, like if we talk about question number second. this some of the questions which that are related to the previous lecture also, but we will discuss that one too. Okay, that question number one, I think it is you can solve this one. Okay, okay, huh. So you can solve homework, I guess. Now, question number second. This all questions were asked in the JEE mains, okay, or it are just given officially given by the NTA website only. See, question number two. I'm talking about this because I have not given any question related to EDTA. What is the EDTA? How many EDTA ethylene diamine tetraacetate unit are required to make an octahedral complex with Ca+2? Okay, I think you understood the question. So it is just asking how many EDTA molecules will be required if you want to make a complex compound with calcium plus 2 central metal ion, and it should form a octahedral complex. Okay, so as we can write like Ca+2, oxidation state equals to +2. Okay, and it is saying octahedral complex, and we have given ligand as a EDTA. Okay, now let's see. So first, the structure of EDTA you should know, that is CH2, CH2, and N and N. Okay, but not just this one. See this one. This is lone pair. Okay, now here the main part comes. OO minus C, CH2, CH2, COO minus. Okay, here CH2, OO, C minus. Okay, COO minus, and here also CH2, COO minus. Okay, so if you want to make the octahedral complexes, so we need six. Okay, we need six donor atoms. So see here 1, 2, 3, 4. This is 5 and this is 6. Don't omit this one because this also plays important role while formation. Okay. So 1, 2, you can mark also 3, 4, 5, and 6. So just 1, I guess. Okay. So its answer is 1. Now let's move on to the second question. Or we can take else. This is not tag dot tag. We will take just important questions. So what we have read is understandable clearly. Okay, this color I will teach later. Okay, let's see this one. Which of the complexes is to have the question number 12? Okay, we will see this one. Okay, I will take a new page. Question number 12. For finding which of the complex compound have lowest delta naught value, that is this value, we will check it out. Delta naught equals to lowest. We have compounds CONH3 6 6 6 6. So it is quite similar molecules that are octahedral, and just we need to think about the ligand. Okay, so let's see, try to solve. See, here all these are same. Okay, this metal atom doesn't involve in that lowest delta value value calculation. We will check ligand. Okay, ligands check. So 3NH3 we are seeing. Okay, and one is CF6. Okay, now here is the only difference because all have coordination number equals to 6. All have the oxidation number as 3 - 3. Okay, oh sorry, +3. So let's see. Now, the magnitude of delta naught varies from a stronger to weaker ligand. Okay. What I'm trying to say is the delta naught value varies uh, varies from stronger to weaker ligands. Okay. So it will depend upon the type of the ligand. Now, according to the question, we have fluorine and NH3 as a ligand only, but I have not taught this one, but you know that spectrochemical series which defines or which gives us the stability about the ligand property, that is strength, if it is a weak or strong. So that fluorinative ion is a weaker weaker ligand as compared to the NH3. Then NH3 we can write. Okay. So I have written that the value varies from stronger to weakened ligand. So as fluorine is a weak ligand, so it will have a lowest delta knot value. Okay. So if delta knot directly proportional to stronger, I can say that how much it will be stronger, that will be delta knot value, stronger ligand. So it will be F6 only. Now let's move on to the question number 13. Okay, let's see. Again, I will take a next page. So what question number 13 is saying? Question number 13 is saying that nickel, okay, we have the electronic configuration, atomic number. Okay, we know that one also. If it is not written also, that it is okay. Okay, nickel equals to, that is 28. Okay, combines with a uninegative monodentate ligand to form a diamagnetic complex NiL4 2 negative. Okay, from the question only I am able to understand what type of complex compound will be formed. It is a monodentate ligand. Okay, so no think about E and diamine or that at all this part. The hybridization involved and the number of unpaired electron present. Okay, just we need to make the that d orbital structure, that orbital diagram only. Okay, so it is asking orbital diagram. Without this you can't not solve this question. Okay, so we have Ni and it's as this is -2, so I'm able to say this is Ni+2. Okay, this is oxidation state is equals to +2, since the complex is given diamagnetic, is a diamagnetic. Now all electrons are paired in inner 3D other orbitals to provide the electronic configuration. As we just need to make that orbital diagram of Ni+2. Ni+2 is equals to, how it can be solved like argon. Now the outermost electron we need to fill in at a d orbital. How we can fill? First make the 5 orbital. Okay, like this one. This will contain 8 orbitals like this. Okay, so or we need to fill like this one, I guess. Okay, let fill after that one. First make the general electronic configuration. This one, this one, this one, this one. Okay, so this is 5, 6, 7, 8. Okay, 8 molecules come inside. Now we need to add 4 more. This is 1, 2, 3. This is 4p and this is 4s for our uh, connection of this L. Okay, now we will need to make the complexes compounds. Okay, so it is saying that the hybridization involved and the number of unpaired electron present in the complex. Okay, let's see. So we can do here one thing, that we can place it here only, so it will become like this: 1, 2, 3, 4, 5, here, 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 here. So this will be clear. Okay, so we can place here one molecule, here 4s, one molecule, and this p molecule, p orbital, we can place some more. Okay, so I guess now we can add this like this one, this one, and this one. So we will get, okay, we will need 2 from here. So this is DsP2. Okay, so DsP2 hybridization can be occurred here. So why I'm trying to say that DsP2 we can also consider as a sp3 also tetrahedral, but see, as L minus we have given this L minus. Okay, so it can be a strong field ligand like Cn negative. Okay, so the hybridization for this is DsP2. As you know that for strong field ligand we use the inner orbital complexes, so you need to check that also. So number of unpaired electrons equals to 0, as we have paired that 2 electrons which were paired, which were unpaired. Okay, so you need to check that. So an example like that, okay, DsP2 and 0. So this is the answer. So we have completed question number 13 also. Now let's move on to the one question, question number 14, I guess. We can discuss about more questions later. Question number 14. So what question number 14 is trying to say? A number of incorrect statements are, okay, the pi bond between metal and carbonyl compound reduces the bond order of CO in carbon monoxide. Okay. Second one is dz square orbital of central metal atom or ion is used in dsp2 hybridization. Cn negative is a pi acid ligand and all negative ligands are stronger than neutral ligand. Okay, see. This one is the correct statement according to me. Okay. The pi bond between the metal and carbonyl reduces the bond order. Okay. You know that. Now, talking about B, dz square orbital of central metal atom. This does not take part. Okay. This does not take part in the dsp2 hybridization as we have seen just in now only. Okay. Now, the Cn negative is a pi acid. Okay. This one is also true. So I guess this B is not correct. Okay. So we can check multiple statement also. So why I'm saying that B is not correct, because if we make a compound like this, let's take a previous example only. That was 3D, 4S. Okay, it was many 1, 2, 3, 4, 5. I am taking the last one now, and this is comes P. Okay, so we have taken this two. Okay, P2. This is S, and we are taking D. So the orbital which takes part in the dsp2 is not dz square. Okay, it is not there. This is a dx square minus y square. Okay, this is the correct configuration. So B is not correct. So our answer will be B. Now try to solve 1 to 2 more questions, so it will be more clear about this chapter. Okay, let's take some example question. Okay. Okay, let's take question number 17. Question number 17. What question number 17 is trying to say? Question number 17 is saying we have given certain compound that is NiCl4, which contains 2 negative charge, then PtCl4 2 minus, okay, and PtCl4. Okay, it looks similar all three. Okay, now it is saying okay, we need to identify the high spin, low spin. Okay, about this one. See how we check the high spin or low spin. See, for this first one, NiCl4, Ni is a 3D series element. Okay, you all know series element. Okay, and the ligand attached to this one is chlorine negative, and it is weak ligand. In the previous question, we discussed this one. Okay, okay. So if nickel is a 3D element, okay, so it will form a complex compound, but due to this weak ligand, it will have a high spin. Okay. Now for that PdCl4, PdCl4, it is a 4D series. PD is a 4D series, and Cl is a that weak ligand only. But there is I have told you about certain limitations also about that theory, valence bond theory. Okay, and the naming. Sorry, how we use the ligand in that compound. Okay, so it will use it as a low spin complex. Now talking about PtCl4. Now PT is a 5D series. Just it is the same group element. Trying to say just down. Okay. Now here chlorine negative is a weak ligand. If you say that now, see weak ligand. So this will be wrong. Why? See, in this case, for 5D series elements, that is PT, here chlorine minus acts as a strong field ligand. Although it is a weak field ligand, but it is acts as a strong ligand here. Okay. So for PT, PD, okay, like for PT, PD, okay. So here I have written weak ligand, but it is not. It is also a strong field ligand. Only for 3D series, it acts as a high weak ligand, although it is a strong field ligand. So you can note it down also for 5D series, the chlorine acts as a strong field ligand. So it will also be an low spin complex. Okay, low spin complex. Okay, so what is the that is high spin? Okay, high spin, low spin, low spin. So C will be the answer. Okay, that's it for now. So we have discussed some of the questions, some important question, and for now, we can uh, end it up till here only, and we will see in the next lecture. So just practice. You can check this uh, PDF from online Google only, and that is Mathongo website. I have taken from there only. So just practice these questions. Thank you all of you. We will meet in next lecture.